Hello everyone, this is the tutorial series on data structure and algorithms. Myself Dr. Bora, and this is the lecture number 3, that is asymptotic analysis of algorithm. And in the lecture number 2, we have gone through the complexity of an algorithm, its base case, worst case and average case. So if you have not already gone through it, then I'm giving the link below in the comment box, so go through it. And one thing that I'm going to ask you one question at the end of the video, and so I suggest that go through this video, watch this video very seriously so that you will be able to answer that question and comment your answer. So let's begin our lecture today. So asymptotic analysis. You know, in mathematical analysis, what does it mean by asymptotic analysis? In mathematics, asymptotic analysis, which is also known as asymptotics, is a method of describing limiting behavior. Okay, so whenever you have got a term like asymptotic or asymptotic, then do remember that this is actually talking about the limiting behavior of that function. Okay, so now in our case, as this is the asymptotic analysis of algorithm, so asymptotic analysis of an algorithm refers to defining the mathematical foundation of its runtime performance. So here we try to define the mathematical foundations. Mathematical foundation means, you know, upper bound, lower bound, like that. Now, as we have already seen in the last lecture that we have base case, average case, worst case. So using asymptotic analysis, the base case, average case, worst case scenario of an algorithm may be evaluated. Like you have upper bound, lower bound, okay, in that way. Now, do remember that asymptotic analysis is input bound. Well, what does it mean exactly? So input bound means that it is totally dependent on the number of inputs. If there is no input into the algorithm, it is concluded to work in a constant time. Got it? So other factors are considered constant, only it is dependent on the input. So asymptotic analysis is input bound. Now coming to the different asymptotic notation. I hope this asymptotic analysis, this technical term is clear to you, where we try to find the limiting behavior of that function. Now, we do have different notation for this asymptotic analysis. The common notations for measuring the running time complexity of an algorithm are big O notation. This is pronounced as big O. Do remember. Okay. Big theta. This one is big omega notation, then big theta notation. So first one is big O, second one is big omega, and third one is big theta notation. And do remember that here small o, small omega, small theta, they have different meaning from big O, big omega, big theta. So don't confuse it. I will cover those big small theta, small omega, small o in next lecture. But currently, big O, big omega, big theta, as they are frequently used in the algorithm, we are going to cover it in today's lecture itself. So, big O notation. What does it mean? Big O notation. It defines the upper bound of an algorithm. You know, upper bounds means that value which is greater than the values of that function for the input parameter. Okay. So it will be more clear if you look at this diagram. In the diagram, you will see that we have this x-axis and we have this y-axis. And in this x-axis, we have input size. Means in this direction, input size is increasing. And in this direction, rate of growth is increasing. So you will see that at point K, this Zn function has values which are greater than Fn, and this is very clear from this diagram. You see that from this point up to this point it is okay, but after this point the the values of Zn is greater than Fn. So we can say that when this point is crossed, then Zn is acting as an upper bound of Fn. So this means what? Big O of Fn will be Zn for all there exists C1 greater than 0. You will see that there is a constant C1 here, C1 into Zn. I am writing like that. And NO such that Fn is less than equal to C1 Zn for all n greater than n naught. So this K, okay, so this particular K where it touches is our n naught point. When n naught value occurs, after that we will have a upper bound Zn for the Fn. So that's why big O of Fn we can write it as a Zn such that there exists C1 greater than 0 and a point n naught, and Fn is less than equal to C1 Zn for all n greater than n naught. Is this clear? Okay, so it's big O notation working as an upper bound of the algorithm. So it bounds a function only from the above. Clear? Now, big omega notation. Okay, so this big omega notation expresses the lower bound of an algorithm in running time, and it measures the base case time complexity or the base amount of time an algorithm can possibly take to complete. So this is the base case. If we talk about the complexity analysis, then this omega will be the base case. Now in the first case, omega big O, you will see that is the upper bound. Now omega is the lower bound. See, again consider this figure. This is the rate of growth axis and this is the input side. Now this K means this point here is the n naught. When there exists C2 greater than 0 and n naught such that Zn will be always less than Fn when it crosses that n naught point. Okay, then we will say that omega of Fn is our Zn. So I am repeating it again. Omega of Fn is equal to Zn when there exists C2 greater than 0 and n naught such that Zn is less than equal to C2 Fn for all n greater than n naught. Okay, I am writing here C2 dash because I am assuming that C2 dash is equal to 1 by C2. From this equation, if I divide both sides by C2, then here we will have Fn is greater than equal to 1 by C2 Zn and say 1 by C2 is equal to C2 dash. Clear? So now Zn is acting as a lower bound. Okay, and in this case, lower bound is expressed as a omega notation. Clear? Now coming to theta notation, and theta notation is the combination of both upper bound and lower bound. So the notation theta n is used to express both the lower bound and the upper bound of an algorithm running time. Okay, so same figure, rate of growth, input size. Now this is our Fn function. Now you will see that here Fn has upper bound also for some C1 Zn. It is being bounded above by this Zn, and for some constant C2, it is again bounded below by Zn. So theta of Fn is equal to Zn if and only if Zn is equal to big O of Fn and Zn is equal to omega of Fn for all n greater than n naught. So this means that, as you know from this graph, this C1 Zn, this is the upper bound and this is C2 Zn is the lower bound. So we mean to say that Zn is acting both as an upper bound and lower bound for some different constant, of course, but the point from where it acts as both upper bound and lower bound is n naught. Okay, so is this clear? So do remember that theta of Fn exists only when both upper bound and lower bound exist. So theta of Fn is equal to Zn if and only if, this IFF stands for if and only if Zn is equal to big O of Fn and Zn is equal to omega of Fn for all n greater than n naught. Clear? So guys, I think this big O notation and omega notation and this theta notation is very clear to you now. So if any doubt still exists, then do comment me, then I will of course respond to those comments. Clear? Now, question from today's lecture. Okay, so today's question is, which asymptotic notation represent the upper bound? I'm repeating it again. Which asymptotic notation represent the upper bound? Comment your answer. Okay, then we'll meet in the next lecture, lecture number 4. So guys, if you like this video and if you think this is very beneficial for you, then do subscribe this channel, like and share with your friends. So guys, take care. Bye bye.